is the screencast for Chapter 12. Hey, say hey, Spencer White.
Hi, my name is Spencer White.
It is. So, again, these are solutions for Chapter 12 homework, um, which deal with thermodynamics and thermodynamic processes. So, um, got things here. We went through a number of these in class. We did not go through number 7. The key thing with number 7, I think, is you need to make sure you're thinking about things in terms of absolute temperature, which is Kelvin. So instead of like doubling 20 to 40 Celsius, what you'd have to think about is doubling the energy would be doubling the absolute temperature. So that was 293 Kelvin. That was up to 586. For problem number 9, again, very similar. This is actually using Boltzmann's constant. I know we talked about that in class a little bit. You could think about the change in E thermal is equal to that, but you didn't really need to do a calculation. I'm showing what you could have done. So if the thermal energy decreases by 10%, then the temperature must decrease by 10%. But again, we need to think about that in Kelvin. So if our initial temperature was 293 Kelvin, we lose 29.3 Kelvin off of that. All right, have a good day.
Bye.
So for problem 14, this is actually a rearrangement of pressure equals force over area. And so the net force on the eardrum is 2.5 newtons because we have the pressure which was given, and I can get the area of the eardrum. 15 was a lot of linear units or English units. So I converted to atmosphere, got absolute pressure, and then recognized as this went up what things would be in terms of PSI. So basically was thinking about absolute versus gauge pressure. Problem 20 we went over in class. So again, that was thinking about net pressure and net force. So that means the absolute pressure minus the atmospheric pressures to get the gauge pressure. So P net, F net, and then Newton's second law. For problem 29, again, I think we went through this as well in class. So I drew the process here. You can figure out the final pressure based on information that was initially given. Again, making sure everything's in standard units is the key. Problem 30. This one was not in standard units. That's why I said Tom Brady's a cheater. So essentially, if having the gauge pressure of 13 psi at your initial temperature of 300 Kelvin. So that is going to determine the absolute pressure. You add the atmospheric pressure, which is 14.7 psi, and you get 27.7. So then you can use ratios. We talked about that in class as well. So the temperature goes down, so the pressure is going to go down. But it's the absolute pressure that's going to go down. The atmosphere is not. So the new absolute pressure is 26.1 psi. So then we have to subtract off the atmosphere, and we get that the ball's pressure is lowered quite a bit. So actually it is interesting because for a fairly small change in absolute temperature, the gauge pressure does also change by quite a bit, going from 13 to 11.4. For problem 33, this was an isovolumetric process, so something is being compressed at this point. Or pardon me, not compressed, something is going to a lower pressure. That means its temperature also has to be lower. So I ended up calculating the temperature by using a version of PV equals nRT, making sure the volume and pressure were in standard units. Problem 34, I think we went over in class, so an isothermal process is hyperbolic. Problem 35, we also went over in class, so that's an isobaric process. So if the volume is a third at the same pressure, then the temperature must also be a third. So we started at why did I change that? Oh, because it's 900 Celsius. 1173 Kelvin. So a third of 1173 Kelvin is 391 Kelvin, which is 118 Celsius. So I forgot to do the conversion initially there. I just read 900 and I didn't look at the units. So 391 is 1/3 of 1173. And then you can plug those in and get the number of moles. For problem 36, they did this in class also. Work done on the gas is the area under the line. And since the volume is decreasing, the work is positive. The last one we talked about in class also, it's the rate of heat flow across a material that has different temperatures on each side. So that depends on the temperature difference, the area, some constant for the material, and then the distance or the thickness of the material, which is L, which is a little bit odd. And this K for wood was in your book. So hopefully that makes sense. If you have any questions, again, hopefully you can ask me before your test.